Consider the polar equation r is equal to 2 times 1 plus cosine theta. So how can we find all the points where they could be a horizontal tangent line or vertical tangent line in this polar equation? What do we need to do? Well, first, we need to find the derivative dy dx, which is dy d theta divided by dx d theta. So when a numerator is equal to 0, that's where we can get a horizontal tangent line. And when the denominator equals 0, a vertical tangent line may be present. So let's begin by finding dy dx in this problem. So the first thing I'm going to do is find dr d theta. So dr d theta is the derivative of this equation with respect to theta. The derivative of 1 is 0. The derivative of cosine is negative sine. So we could say that dr d theta is negative 2 sine theta. Now let's find dy d theta and dx d theta. So let's start with this expression. X is equal to r cosine theta. Now let's differentiate both sides with respect to theta. So we're going to have dx d theta. Now r is a function of theta, and theta is a variable. So we have two variables in this equation. Therefore, we need to use the product rule. And recall that the derivative of u times v is going to be u prime v plus uv prime. So the derivative of the first part, which is r, that's going to be dr d theta, times the second part, which we'll leave it as cosine, plus the first part, times the derivative of the second part. The derivative of cosine is negative sine. Now let's do the same thing for y is equal to r sine theta. So let's focus on this equation. So dy d theta is going to be the derivative of r, which is dr d theta times sine plus the first part r times the derivative of the second part, which is the derivative of sine is cosine. And so we have that. So now we can write an expression for dy over dx, which we said it's dy over d theta divided by dx over d theta. And here is dy over d theta. Now I'm going to replace dr d theta with negative 2 sine theta. And then it's multiplied by sine plus r cosine. And we can see that r is equal to that expression. So that's 2 times 1 plus cosine times another cosine theta expression. And then it's divided by dx d theta, which is all of this. So we have dr d theta again, which is negative 2 sine theta, and then times cosine theta, plus, or rather minus, because of that negative sign, and then r, so 2 times 1 plus cosine, and then we have sine theta. So now that we have a general expression for dy dx, we can find the location of the tangent lines. So let's start with the horizontal tangent line. Let's set the numerator equal to 0. So simplifying this expression, we have negative 2 sine squared theta, and then we have cosine times 1 times the 2 in front, so that's plus 2 cosine theta. And then cosine times cosine is cosine squared times the 2 in front. So that's plus 2 cosine squared theta. Sine squared is 1 minus cosine squared. And all of this is equal to 0. If we distribute the negative 2, we're going to have negative 2 plus 2 cosine squared theta. So now at this point, what we need to do is combine like terms, and let's write it in standard form. So we can add those two. So we're going to have 4 cosine squared theta plus 2 cosine theta minus 2 is equal to 0. Now at this point, I'm going to divide everything by 2. So this becomes 2 cosine squared theta plus cosine theta minus 1 is equal to 0. At this point, we can factor the expression. So if we multiply the leading coefficient by the constant term, we'll get negative 2. And two numbers that multiply to negative 2 but add up to the middle coefficient, 1, is going to be positive 2 and negative 1. So we're going to replace 1 cosine theta with 2 cosine theta plus a negative 1 cosine theta. And then we could factor by grouping. So in the first two terms, let's take out the GCF. The greatest common factor is 2 cosine theta. 2 cosine squared divided by 2 cosine, that's just going to be cosine theta. And then 2 cosine theta divided by itself is plus 1. Now for the last two terms, we can factor out a negative 1. If we do, we're going to get cosine theta plus 1. Next, we need to factor out cosine theta plus 1. So we're going to write it once. And when we take it out of this term, we're left with 2 cosine theta. And if we factor out of this term, we're going to be left with negative 1. Now you may want to write down this equation for dy over dx, because to get extra space I'm going to delete it now, but I will refer to it later. And when finding the vertical tangent lines, I'm going to set the denominator, this part, equal to 0. So just keep that in mind. If anything, you can always rewind the video. So what we're going to do is set each factor equal to 0. So first we're going to have cosine theta plus 1 is equal to 0, and then 2 cosine theta minus 1 is equal to 0. So if we add 1 then divide by 2, we can see that cosine theta is 1/2. Now for what angles is cosine theta 1/2? Cosine is positive in quadrants 1 and 4, and the reference angle is pi over 3. Cosine pi over 3 is 1/2, and cosine 5 pi over 3 is also 1/2. Now, if we subtract both sides by 1 on the left side, we can see that cosine theta is negative 1. So what angles will give cosine a negative 1 value? Cosine pi is negative 1. So these three angles potentially could be the location of a horizontal tangent line. We're not sure yet, but we're going to have to check it later. But for now, we're going to write down these values. Now the next thing we need to do, in order to find a point in polar form, so that is in r comma theta form, we need to calculate r. We have the values for theta. And so recall that r, in the beginning we said it was 2 times 1 plus cosine theta. So if we plug in pi, cosine pi is negative 1. So we're going to have 2 times 1 plus negative 1. 1 plus negative 1 is 0. So we're going to have the point 0 comma pi. So these are the potential horizontal tangent lines, at least the points where those tangent lines are located. So the first potential horizontal tangent line is located at 0 comma pi. Now for the other ones, we have cosine pi over 3. Cosine pi over 3, we know it's 1/2. And 1 plus 1/2, that's 1.5, times 2, that's 3. So the next potential horizontal tangent line is at 3 comma pi over 3. Now cosine pi over 3 and cosine 5 pi over 3, they're both equal to 1/2. So they will have the same r value. So this is going to be the third point of interest. Now let's focus on the bottom part of the equation for dy over dx. And so we had -2 sine theta cosine theta minus 2 times 1 plus cosine theta times sine. So that's equal to dx over d theta. And we're going to set that equal to 0 to find the locations of any vertical tangent lines. So what should we do at this point? Well, let's rewrite this expression. And let's distribute sine. So we're going to have sine times 1 times -2. So then that's just going to be -2 sine theta. And then it's going to be sine times cosine times -2, which is -2 sine theta cosine theta. So now we need to combine like terms. So we can combine those two. And so we're going to get -4 sine theta cosine theta, and then minus 2 sine theta. And so that's equal to 0. Now let's divide everything by -2. So this becomes 2 sine theta cosine theta. If you want to show your work, for those of you who don't like to skip steps, you can do this. And then you're going to get +2 sine theta cosine theta plus sine equals 0. At this point, factor out the GCF. The greatest common factor is sine theta. And so if we divide this by sine, we're going to get 2 cosine theta. And sine divided by itself is +1. And so this is what we now have. Now let's set each factor equal to 0. So we have sine theta is equal to 0 and 2 cosine theta plus 1 is equal to 0. Sine is 0 when theta is equal to 0 degrees, because sine 0 is 0, sine pi is also 0, and sine 2 pi is 0. However, 2 pi and 0, they're the same, so we don't have to worry about 2 pi. Now for this one, we need to subtract both sides by 1. And so we're going to get 2 cosine theta is equal to -1, and then divide both sides by 2. So cosine theta is -1/2. Now this will happen when theta is 2 pi over 3 or 4 pi over 3. Cosine is negative in quadrants 2 and 3. And so we have these angles: 0, pi, 2 pi over 3, and 4 pi over 3. Now we need to determine the corresponding r values. So let's use this equation again. So when theta is 0, we're going to have cosine of 0, which is 1. 1 plus 1 is 2. 2 times 2 is 4. So we have the point r comma theta, so that's 4 comma 0 degrees. Now for the next one, when theta is pi, we already did that. We're going to get 0. So we're going to get 0 comma pi. And then at 2 pi over 3, cosine 2 pi over 3, that's -1/2. So 1 minus 1/2 is 1/2, and 2 times 1/2 is 1. So we're going to have the point 1 comma 2 pi over 3. Cosine 2 pi over 3 and cosine 4 pi over 3, they're both equal to -1/2. So if you plug in cosine 4 pi over 3, the result will be the same, +1. So here's the other potential vertical tangent line, 1 comma 4 pi over 3. So are we finished? do we have all of the tangent lines in this example? Are there any issues? Now notice that these two are the same. So what does that mean? How can they both be a horizontal tangent line and a vertical tangent line? That's not possible. So we need to figure out what's going on here. Now, let's go back to dy over dx. We're going to take the limit as theta goes to pi of dy over dx, which is, we said it was negative 2 sine theta times sine theta plus 2 times 1 plus cosine theta times cosine over this stuff. Now the way we got this answer was by setting the numerator equal to 0. And the way we got this answer was by setting the denominator equal to 0. Therefore, if we plug in pi at this point, we're going to get 0 over 0, which that could be 0, it could be infinity, it could be doesn't exist, we don't know. If we get, let's say, 0, then that means that it's a horizontal tangent line. If we get like infinity, which is basically like 1 over 0, that's like undefined, then it could be a vertical tangent. So we need to evaluate this limit, and we're going to have to use L'Hopital's rule to see if it's equal to 0 or infinity or something else. Maybe it's equal to 5 or some constant. Either case, it won't be a horizontal tangent or a vertical tangent. So let's simplify this expression first. So this is going to be negative 2 sine squared theta, and then distribute into 2 and a cosine. So 2 cosine theta times 1, that's just plus 2 cosine theta, and then 2 cosine times cosine, that's positive 2 cosine squared. On the bottom, we're going to have negative 2 sine theta cosine theta, and then negative 2 sine theta times 1, that's negative 2 sine theta, and then times cosine, that's negative 2 sine theta cosine theta. Now keep in mind, we already simplified this expression when getting these answers. I'm just going to put it in a certain form. So I'm going to skip this step and go to the part where we had this equation, where it was 4 cosine squared theta plus 2 cosine theta minus 2. You can go back in the video and see how I converted this expression into this expression if you want to retrace the steps. Now, I'm going to use the double angle formula. Sine 2 theta, I'm just going to write it here, is equal to 2 sine theta cosine theta. So this is negative sine 2 theta, and this is another negative sine 2 theta. So combining those two, we have negative 2 sine 2 theta, and then minus 2 sine theta. So in this form, I'm going to use L'Hopital's rule. So I'm going to differentiate the top and the bottom with respect to theta. So I'm going to have the limit as theta goes to pi, and then it's going to be 4, and then times the derivative of cosine squared. So that's going to be times 2 cosine theta to the first power, and then differentiate the inside. The derivative of cosine is negative sine, and then the derivative of 2 cosine theta, that's negative 2 sine theta, and this is a constant, so that goes to 0. The derivative of sine 2 theta is going to be cosine 2 theta times the derivative of 2 theta, which is 2. And the derivative of sine theta is cosine theta. Now I'm just going to simplify this before I replace theta with pi. So I have negative 8 sine theta cosine theta on top, minus 2 sine theta over negative 4 cosine 2 theta minus 2 cosine theta. So now let's replace theta with pi. So sine of pi is 0, cosine pi is negative 1, so this is going to be 0 as well. Now cosine 2 times pi, or cosine 2 pi, that's positive 1, and cosine pi is negative 1. So we're going to have 0 minus 0 over negative 4 plus 2, which is 0 divided by negative 2, and so that's 0. So because dy dx is equal to 0, we're going to have a horizontal tangent line. We got a 0 in the numerator. If we had a 0 in the denominator, then it's undefined. That would correlate to a vertical tangent. So we don't have a vertical tangent at 0 comma pi. Instead, we have a horizontal tangent at 0 comma pi. Now let's go ahead and graph the polar equation 2 times 1 plus cosine theta. And you could use like an online graphing calculator. I'm going to post a link in the description section of this video that explains how to use that online calculator to graph an equation like this. So feel free to check that out if you're interested. So this is the general shape of this graph. It looks something like that. Now, as you can see, we have a horizontal tangent here. Which of these points correspond to that particular horizontal tangent line? Well, if we draw an angle, what is this angle? That angle is in quadrant 1, so that has to be pi over 3. And it's going to have a radius of 3. So this is 3 units from the center. That's how long this segment is. And it's at an angle of pi over 3. So this corresponds to 3 comma pi over 3. Now what about this horizontal tangent line? If we draw a line between the origin and the tangent line, this angle, that's a negative angle, but this angle here, notice that it's 5 pi over 3. And so this particular horizontal line corresponds to the point 3 comma 5 pi over 3. Now we can see that we have 3 vertical tangent lines. Now this particular vertical tangent line, if we draw a line from the origin to that tangent line, you can see it has a radius of 4, and this line is at an angle theta, which is 0 degrees. So that has to be 4 comma 0. Now what about this one? So what is this angle? That's an angle in quadrant 2. 2 pi over 3 is in quadrant 2. So that vertical tangent corresponds to 1 comma 2 pi over 3. And notice that this line segment is short because the radius is 1 compared to a radius of 3 or even a radius of 4. So we can see why the r value is so small. So this has to be 1 comma 4 pi over 3 because it's located in quadrant 3. So we can see that we have 3 vertical tangents, not including that one, and so far 2 horizontal tangent lines. So where's the horizontal tangent line that corresponds to 0 comma pi? Do you see where it is? For one thing, r is 0. So the distance between the origin and the horizontal tangent line is 0, which means that the horizontal tangent line is at the origin. And if you look at the graph, at the origin it converges like this. And on the bottom side, it does the same thing. So notice that at this point, it's becoming horizontal. So here is the horizontal tangent line. It's right at the origin. And so it's at 0, pi. And so that's it for this video. Now you know how to identify the location of any horizontal tangent lines or vertical tangent lines in a polar equation. Now, one thing I do want to mention before I end this video is if you need to find the points in terms of x and y coordinates. So recall that x is r cosine theta and y is r sine theta. So let's use this one as an example, 3, pi over 3. So we have it in the form r, theta. So r is 3, theta is pi over 3. So x is just going to be 3 cosine pi over 3, and y is 3 sine pi over 3. Cosine pi over 3 is 1/2. Sine pi over 3 is the square root of 3 over 2. So we could say that this horizontal tangent line is located at the point 3 over 2, 3 square root 3 over 2. So you can write all of these points in rectangular form as opposed to polar form if you want to. And so that's it for this video. That's all I got. Thanks for watching.